So this is the lecture for Chapter 8, which is the periodic properties of the elements. The text pages where this information comes from is written right on the slide. Please read and outline that before you watch this lecture. We're going to start with the father of the periodic table, who is Dmitri Mendeleev. He is credited with coming up with the idea of the periodic table. There were some other arrangements of the elements before him, but he is really the founder of what we know of as a periodic table today. His table was not completely correct. He ordered the elements using atomic mass, so he put them in order of increasing atomic mass. This is not what we use today. Today we use atomic number. We organize the elements by increasing atomic number. But when Mendeleev organized the elements according to atomic mass, he did find a repeating pattern of properties. Really, it was every eighth element the properties would repeat. So he eventually organized his elements into 8 columns, and we'll look at that in a second. The periodic law is the idea that when the elements are arranged in an order, in this case we're talking about of increasing atomic mass, but it could also be increasing atomic number, you get the properties that recur periodically. So all the first column elements are going to be similar, the second column, so on and so forth. Mendeleev used these properties to predict the properties of undiscovered elements. That was really one thing that separated Mendeleev from other people who were coming up with periodic tables at the time. He was able to leave spaces in his table where he knew an element was going to come around, going to be discovered, and it actually did fit into where he wanted to put it. Some elements did fit, some did not. Some elements were discovered that caused us to rethink the periodic table, and that is how we came up with organizing according to atomic number instead of atomic mass. This is just a little insight into his periodic table. You can see there's 8 groups. These RHs, R2O, is how this element would bond when it makes an oxide and when it makes a hydride. So he has, as you can see, group 1 here, and the first 3 are actually correct. That is what they are today. And you can see a lot of this kind of falls in with where it falls in the modern periodic table. If you notice, there aren't as many elements on this table because there weren't as many elements discovered at the time when Mendeleev made this table. Mendeleev's periodic law allowed us to predict the properties of elements based on their position. It did not explain why the elements had these properties. He could just tell that if it's in the 1A, it's going to be reactive. He could not explain why. Quantum mechanics is the theory that explains why the periodic trends and the properties exist, and this has to do with the quantum mechanical model of the atom, the position of the electrons in the atom, which we know now is the main factor when determining the properties of an element. Experiments by Stern and Gerlach showed that a beam of silver atoms is split in 2 by a magnetic field. I'm going to show you a picture of that experiment in a second. This experiment revealed that electrons spin on their axes, kind of like the way the Earth spins. So very similar to the way the Earth moves, the electrons are spinning on their axes as they rotate around the nucleus. So exactly like the Earth. The Earth is spinning on its axis as it rotates around the sun. This spinning creates a magnetic field that the electrons give off. If there is an uneven number of electrons, or if there's an even number of electrons, half will have a magnetic field pointing up and the other half will have a magnetic field pointing down. You can think of it as north-south pole, the magnetic poles of the Earth. So the electrons are going to pair up, basically one pointing north, one pointing south. So if we look at the Stern-Gerlach experiment, what we have here is basically the mechanism to generate the silver beams, the beam of atoms. It's going to pass through a slit and a piece of metal, and then that beam was then passed through a magnetic field. It has a north side and a south side. And when you pass that beam through, the beam actually split in half. And what we discovered is the positive one half, the electron spinning to the south side actually because they are attracted to the opposite. Half of them gravitate towards the north magnetic field, half of them gravitate toward the south magnetic field. So this told us the electrons are spinning in completely opposite directions. The way we knew that they were completely opposite is the same number of electrons in the beam went north as did south. So that means they have to be even in the atom. The Pauli exclusion principle has to do with how these spinning electrons occupy an orbital. No two electrons can have the same set of 4 quantum numbers, which means no two electrons are going to have the same spin in an identical orbital. So if you have one orbital where an electron is pointing or spinning to the north, the next electron that comes in has to be spinning in the exact opposite direction. This is also what governs how many total electrons can fit on each suborbital. You can only have a max of 2 because you have to have one electron spinning up, and then the only opposite to that would be spinning down. You cannot have a third direction there. Knowing this and knowing the number of orbitals within each principal level gives us the maximum number of electrons that can fit in each sublevel. So for example, an S is going to have one orbital. If each orbital can have 2 electrons, the total number of electrons on each S sublevel is 2. In the same manner, you get P has a total number of 6, D has a total of 10, and F has a total of 14. This is really important when writing electron configurations because that is the max number of electrons you can fit in each sublevel as you write the configurations. Once you reach that max, you have to go into the next sublevel. The 4 quantum numbers describe the address and the spin of the electron. It tells you where it is. It tells you exactly where in an orbital this particular electron is. You cannot write quantum numbers unless you are given a specific electron. For example, an orbital diagram with a circle around a particular electron. The 4 quantum numbers are the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. We're going to talk about each one, and we're going to start with the principal quantum number. That symbol is always an N. It's kind of a cursive N. This describes the total energy and also the size of the orbital. So for example, an N equals 1 orbital is smaller and contains less energy than an N equals 2, so on and so forth. Remember that an orbital is not a precise location. Remember, Heisenberg said there is inherent uncertainty with it. So we say the principal quantum number indicates the probable, which in this it says within 90%, distance of the electron from the nucleus. Again, it can measure the orbital size as well as the energy. N can have a value of 1 to 7. We don't need to go higher than 7 right now. Elements don't exist that go higher than 7. And the total number of electrons is 2n squared. The angular momentum quantum number, now the symbols for these can be a little different. You can see M sub L. In this case, I'm just showing a cursive L. As long as you understand what the properties is describing here, the symbol can be translated. The angular momentum tells you the orbital shape or type. This is characterized by the wave shape. So this is where we get the SPDF, the sphere shape of the S, the dumbbell shape of the P. You can see these shapes over here. So what we do is we relate a value or a number to the letter. So if you just remember that the S orbital, the sphere orbital, is 0, and the rest of the orbitals just go up by 1, it's very easy to remember. So an S is represented by a 0, a P by a 1, a D by a 2, and F by a 3. There is a G and H. You generally won't get that high because that's where we're talking about the lanthanide and actinide series, and those aren't really reactive, but they do exist. The magnetic quantum number, M sub L, tells you the energy levels within the subshell. So remember, each subshell can have different energy levels. So the S has 1 energy level, the P has 3, the D has 5, the S has 7. So because there's different levels within the subshell, you have to know where that electron is, which sublevel is it in. And the way you do that is kind of like a number line. So for example, S only has 1 sublevel, so it's automatically always going to be 0. So basically, if you have an angular momentum number of 0, your magnetic quantum number is going to be 0 automatically because you know it's an S. The rest of the numbers depend on where the electron is. Remember, you have to be given an orbital diagram and have a circle of an electron to know where to put it. So what you do, if it's a P, it's going to have 3 orbitals. You always find the middle orbital, label that 0, and then it acts as a number line. Every box to the left is going to be negative. Every box to the right of the 0 is positive, and you just go up by 1. So P is going to have a negative 1, 0, 1. Notice the D, you find the middle box, negative 1, negative 2, and then positive 1, positive 2. And then the F again, find the middle, that is 0, negative 1, negative 2, negative 3, and then all the way up to positive 3. The spin quantum number is the last one, M sub s. This tells you basically which direction the electron is spinning. Is it spinning clockwise or counterclockwise? Is it spinning up or down? We don't really care about the particular direction of the spin. We're just saying this electron is spinning in one direction, the other electron is spinning in the opposite direction. There are only two values for the M sub s, the spin quantum number. It's either going to be positive 1/2 for an arrow going up and negative 1/2 for an arrow going down. You should always fill an orbital diagram with an up arrow first. This chart just summarizes all the different quantum numbers, their names. Notice some of them have slightly different names. They're all translated, they all mean the same thing, but you should know all the vocab. So if you look at an example here, helium only has 2 electrons. So their quantum numbers are actually pretty easy to write. Both the electrons are in the 1s orbital. So using that information, you have a 1s2 electron configuration. You can get the principal quantum number of 1 that tells you the size. It's the big number in front of the electron configuration. Since it's a 1s, the shape is going to be a 0. Since it's a 0, it only has one orientation, so again, that's a 0. Remember I told you, if the L is a 0, the M sub L is automatically a 0. And then finally, the only difference between the two helium electrons is one is spinning up, one is spinning down. So one is positive 1/2, one is negative 1/2. For electron configurations, they can be written in the ground state or even in the excited state, which we'll see in a little bit. The ground state is when the electron is in its lowest possible orbital, not necessarily the n equals 1 orbital. It is just when it is as low as it possibly can get, when it is as close to the nucleus as it can. The distribution of the electrons is called the electron configuration. It's kind of like a seating chart. It tells you where the electrons are likely to be found. Remember, it is not an exact chart. It is not exactly where this particular electron will always be. It is a chart that shows you where you are most likely to find electrons in this atom. So if we see the 3 parts, the number designates the principal energy level. So this is 1, 2, 3, so on. The letter tells you the shape. S is sphere, P is dumbbell, D, F. And the superscript tells you the number of electrons in that particular sublevel. So if I look here, there are 2 in the 1s, 2 in the 2s, 6 in the 2p, etc. Remember what we talked about before with the maximum number of electrons in S, no matter if it's a 1s, 2s, 3s, can only hold 2. P's can only hold 6. D's can only hold 10. And F's can only hold 14. Once you reach that max, you have to spill over. Notice the end of this, you do not have to have it filled to the max, but once you hit that max, it has to go over to the next orbital. An orbital diagram is just a different method of showing how the electrons are arranged. We consider it a little bit more precise because it shows exactly where in the sublevel it is. You can write an orbital diagram using either a box or a straight line. You should label the box or straight line with the principal quantum number and the shape, and then you fill the box in line with the arrows. You should always start with an arrow pointing up and then fill in with an arrow pointing down. Hund's rule is one of the rules that comes in that tells you how electrons fill the orbitals. Hund's rule is kind of like sitting on a bus rule. If you're going to get on a school bus, you're going to go try to sit by yourself first. You're going to go to the back of the bus and try to sit by yourself. You're only going to sit with another person if you have to. That's kind of what the orbitals do. So if you have equal energy orbitals, like these 3 2p's are all the same energy, it is going to fill by going up, up, up. Once it has no more room, then it's going to go down, down, down. So if you can see here in this 3p, it has one up arrow. The next electron is actually going to go into this box here. And the following one will go into this box here. This is true for the P, D, and F. The D actually feel a little bit weirder. They go up, 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 down, 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 up, up, etc. and so forth. Effective nuclear charge is a very big topic with AP Chemistry. They want you to be able to use this term correctly. It's a very big term for a very easy concept. Effective nuclear charge is just how strongly the positive nucleus pulls on the electron. That's just simply what it is. How much pull does that nucleus have on the electron? There is a magnetic charge or attraction between the negative electron and the positive nucleus. The magnitude of that pull is proportional to the magnitude of the charge in the nucleus. So you can calculate effective nuclear charge by taking the nuclear charge, which is the number of protons, minus the number of core electrons, or the average number of electrons between the nucleus and electron of interest. So if we look at this picture, to get the effective nuclear charge, we look at the nucleus. It happens to be a lithium atom. We know lithium atoms have 3 protons, so that is my start. That would be this number Z here, has 3 protons. Then we look at and we count how many electrons are present between the nucleus and the electron that we're looking at. We're looking at this particular one here. And after I do my orbital diagram or my configuration, I know that there are 2 electrons in between this nucleus and this electron. So that is going to be the S. So what I do to get the effective nuclear charge is I take positive 3 minus 2 electrons to get an overall charge of positive 1. So that nucleus is pulling in that electron with an overall effective nuclear charge of a +1 pull. Effective nuclear charge increases as you go up and to the left. So you are going to find the highest effective nuclear charge in the top right corner, the lowest in the bottom left corner. You can see here some specifics. It's actually measured in picometers. Not really necessary that you know the actual number, just that you know the trend and what effective nuclear charge is and how you can calculate it. Shielding is a concept or a phenomenon that happens in an atom that is exactly what it sounds like. The electrons are shielded, just like, for example, a Spartan shield to protect that soldier from, a sword or a spear or whatever it may be. Electrons intervene or come between the nucleus and the outer electrons. This is the shield or a screen. The outer electrons are no longer able to be pulled in by the nucleus as much, so the electron does not experience the full nuclear charge. So if we look at the picture, the electron of interest is right here. The outside electrons have no effect on this electron. So the electrons in the blue we don't really care about. We're just looking at the electrons between this one and the nucleus. And you can see all these electrons that are present in the green area are going to shield or block out the charge, the pull between the nucleus and this electron. So this electron is not going to be pulled as tightly the more electrons that block it or shield it. So if you look at the difference between chlorine and magnesium, the effective nuclear charge of chlorine, we just take 17 minus 10 core electrons to get a positive 7. And in magnesium, we take 12 protons minus 10 core electrons to get positive 2. You can see that the radii of chlorine is smaller because the nucleus pulls the outer electrons closer because the effective nuclear charge is +7. With the magnesium atom, it's going to be smaller because the pull is only, magnesium is because the nucleus can only pull with a positive 2 charge. If we look at the difference between penetration and shielding, again, it really is exactly what it sounds like. Remember that electrons repel each other. They are both negatively charged. Remember that the nucleus pulls in the electrons because they're oppositely charged. And these forces go down, both the push and the pull, as you move away from each other. So the farther the electron moves away from the nucleus, the less pull it's going to have. This radial distribution graph, what it's called right here, shows that the 2s orbital penetrates more deeply into the 1s orbital than does the 2p. So if we look here, we have the 2s orbital going farther into the region where the 1s is than the 2p does. So it's penetrating more. The 2p electrons experience more repulsive force because they are not penetrating as far into the 1s orbital. They are blocked or shielded from the nucleus by the 1s and 2s electrons. This means that the electrons in the 2s are pulled greater to the nucleus because they are not as shielded. There's less between them and the nucleus. The result is the electrons in the 2s are lower in energy than the electrons in the 2p. The penetration and shielding phenomena, is what gives us the order of the orbitals. It is why they do not just go in a nice orderly fashion. It's because of this. So if we look here, shielding right here, we have the nucleus and these two electrons. These two electrons are blocking the pull of the nucleus or shielding from this electron. If we look at this one, this electron is actually kind of, you can think of it dipped in or penetrated into this, I guess this would be the 1s region, and therefore this electron is feeling the full force of the nucleus here because it has penetrated in. Because of this penetration and shielding, you see that the energy levels are not in a very clear pattern. You would think it would go in order: 1s, 2s, 2p, 3s, 3p. You can see that that works up until 3p, and then all of a sudden, because of penetration and shielding, the 4s is actually lower in energy than the 3d. So when you're doing the electron configurations, this is your order. It goes according to this graph: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, so on and so forth. So this does not go in an orderly fashion. You can actually see as you get farther to the top, it gets more and more jumbled. So obviously that's a very hard thing to memorize. So what you can do is draw something called an Aufbau diagram, which kind of gives you the shell order. So you can actually start with the one on the bottom or the one on the top. It doesn't matter. And you just number it, 1 through 7. 1s, 2s, 3s, 4s. Remember that the 1 does not have a p, so you leave that section blank and then go 2p, 3p, 4p, 5p, 6p. Again, the 2 does not have a d, so you skip. And the 3 does not have an F, so you skip. So you should have a nice little triangle shape to your numbers. You then are going to draw parallel arrows, and the key is to make them parallel. So if you know the fill order up to 3s, which is 1s, 2s, 2p, 3s, and then you draw perfectly parallel lines, it gives you the order of orbitals from lowest to highest energy. You don't have to memorize, you can just follow along. So that order is going to be 1s, and you snake around, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc. and so forth. No need to memorize. If you can draw this diagram, you just have it there for electron configurations. The energy shells are always going to fill from lowest to highest. That's why it's important to know the Aufbau diagram and know what that order is. Orbitals in the same shell have the same energy. Remember that no more than 2 electrons can fill an orbital at a time. And when you're drawing an orbital diagram and they're within the same energy, like the 3 2p orbitals, they're going to fill like sitting on a bus, like Hund's rule. They're going to go up, 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 and then down, down, down. So if we look at the first problem, it says write the ground state electron configuration and orbital diagram of magnesium. So the first step is to determine the atomic number because this gives you the number of protons and electrons. So I figure out the atomic number of magnesium is 12. So when I write the orbital diagram and the electron configuration, I'm going to have to show 12 electrons. I'm going to draw 9 boxes because I know that it's only going to be, that's as much as I need to fill it. And then I just go ahead and put my arrows. So I've labeled the boxes here. Remember, you always start with an up. So you add 1 electron to each box and then you pair them before going on to the next one. So when you pair, you use opposite arrows. So what I would do here is 1 up, 1 down. That's 2. Up, down, 4. For the P's, I would actually go up, 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 down, down, down. So now I have 2, 4, 6, 8, 10. I only need 2 more in the 3s, and my 3p is actually empty. I can then use the diagram to write the electron configuration, or you could do it the opposite way. You could write the electron configuration first and then draw the orbital diagram. The way you do it is the order comes from the Aufbau diagram, remember? Remember that the S is a maximum of 2, P 6, D 10, F 14. So I'm just going to write it out. I'm going to say 1s, I know it can only hold 2. I know I need more, so I go to the next orbital. I know I need more, then I go to the next orbital. And then I just count the superscripts to get the total number of electrons present. So I have 1, 2, 3, 4, 10, 11, 12. This here is showing you noble gas configuration, which we're going to talk about in a little bit. The electrons in the subshell with the highest principal energy level are called valence electrons. They are the outermost electrons. The rest, or the electrons in the lower shell, are called core electrons. We pay attention so much to valence electrons because that is one of the most important factors when determining the physical and chemical properties of an element. We know a lot about the element knowing it has 1 valence electron. So if we look here to look at the number of valence, Krypton has 36 electrons. This is the entire ground state configuration. To figure out which one are the valence, you look at the number of electrons in the highest principal energy level. Remember that the highest principal energy level is the big number in front. So if we look here, I have 1s and 2s and 3s, and I see a 4. Then I see a 3 and then a 4. You would think that you would just go to the end, count the total number there, and there's you're done. That's valence. But it is the total number of electrons in the highest principal energy level. So yes, you're going to count these 6, but also these 2, because these are both in the 4, which is the highest principal quantum number. So the total number of valence here is actually 8. If you know 36 minus 8 gives you 28 core electrons. Rubidium here, you see it's going to be in the noble gas form, and that's actually easier to figure out how many valence. You can see there's only 1, and if we look up here, there's only 1 electron in the 5 quantum number, so that's going to be the number of valence. For the 5s1 electron, the quantum numbers would look like this. So it would be n equals 5, because it's an principal energy level 5. L is 0 because it's an s. ML is 0 because, again, it's an s orbital. And then we know, since it's only the first electron, that the electron is going to be pointing up. So that is plus 1/2. Look here, just summary of the quantum numbers, the number of electrons, the electron configuration, the orbital diagram. So you can go ahead and review that. If you look down here, though, here's the Hund's rule we were talking about. Carbon has 6 valence, or 6 total electrons. So you're going to put 4 in the 1s and the 2s. You have 2 remaining. You are not going to put them both here. But you're going to fill up, up, up. So this is what the orbital diagram looks like. The group number corresponds to the number of valence electrons. That's an easier way of figuring out how many valence it has. This works for the A group elements, not for the transition in the middle. The length of each block is the maximum number of electrons a sublevel can hold. I'm going to show you that in a second. And the period number actually corresponds to the principal energy level you start with, the S. So if we look at a periodic table here, this is separated into the blocks. This is the S block, P block, D block, F block. Remember, the S has a maximum of 2 electrons, or has 2 sublevels. Look at this, 1, 2. The P can hold a maximum of 6. 1, 2, 3, 4, 5, 6. D can hold 10, F can hold 14. It actually all works out. Group numbers tell you the number of valence. So group number 1A has 1, 2A has 2. Skip over the transition, 3 has 3, 4, and so on. And then the period across tells you where the S starts with. So if you think of this as a graph, this whole row is going to be the S1. And then the period number tells you which principal quantum number it's in. So 1s1, 2s1, 3s1, 4s1, etc., and so forth. If you look at this periodic table, it gives you an idea of how these fill. The D actually fill very weird. So if we're being very particular about a D, they do not go across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That kind of has a different concept, and you'll kind of know that you're talking about that when you talk about the different concept. Everything else goes in order. This is showing you the noble gas configuration. Remember, the noble gases are the ones in 8A. And what you do is, if I'm trying to find the noble gas configuration of P, I locate P on my periodic table. I immediately go to the row above it, find the noble gas there, which in this case is Ne, and I write that in brackets. I then follow my path from Ne to P, and I see which blocks I go through. So if I go down to the third row, I'm going to have to go through the 1s and 2s. I know it's 3, so instead of 1s, it's going to be 3s2. You just don't write it 3s1, 3s2. It's kind of like combining. And then I'm going to go here, which is the P1, P2, and I'm going to stop at the 3p. And again, it's row 3, so it's going to be 3s2, 3p3. If you count the number of valence, you look, 3 is the highest quantum number, principal quantum number. So if you count the total in there, you're going to get 5. The D block elements, the principal energy is 1 less than the valence. So if it's in row 3, I'm sorry, that won't work. If it's in row 4, the number in front is going to be a 3. So if we look here, it's in row 4, period 4, the D block is going to be 1 behind, which is 3, and the F is actually 2 behind the period number. So if it's in period 6, it's going to be 4F. So again, if we look at the electron configuration of arsenic, AS, I go to the row before, locate the noble gas, AR, put that in brackets. I then follow the path from AR to AS. I see I go through the 4s1, 4s2, write that down. I'm going to go entirely through the D block, but I'm going to remember it is not the 4D, the D or the one behind. It is the entire D block, which is 3D10. And then finally I stop at the P1, P2, P3, so it's going to be the 4P3. Notice I have 5 valence electrons because the 3D do not count. They are not the highest principal energy level, so you only count these 2 and these 3. Giving you a little practice of writing short electron configurations, which is just another way of saying noble gas. So if we were to do that, the answer should be Ne, 3s1, and then here's the orbital diagram. Go ahead and practice that on a scrap piece of paper and then check your work. Elements in the same column have similar chemical and physical properties. These properties repeat. This is a major part of the periodic table. The reason these properties are the same in the block is because they have the same number of electrons. The electrons are in similar patterns. They're located in similar orbitals, so that is why they behave the way they do. So if we look here, here's just groups of the periodic table. We have the alkali metals, alkali earth, transition metals, rare earth are down here, just general nonmetals, halogens, and inert or noble gases. The number of valence electrons largely determines the behavior. Since the number of valence follows a periodic pattern, the property should also be periodic or repeating. Quantum mechanical calculations show that 8 valence electrons should result in a very unreactive atom. If you think about all elements want to have 8 valence electrons, and everything they do is to get them 8 valence electrons. And if it already has 8, it really doesn't have to do much, which is what happens with the noble gases. They already have 8 valence electrons. They're very stable. They like the way they are. They don't want to change. They don't react. Conversely, if you think about halogens or alkali earth metals, their alkali earth metals have 1 valence electron. That's far from 8. They want to do something very readily to get 8. Same with the halogens that have 7. Many metals and nonmetals form an ion. And what ion is formed is very predictable based on its group number. So again, the ion is, you can think of it as what's going to happen to this number of valence to get to 8. So for example, 1A has 1 valence electron. It is going to be easy for it to lose an electron to get a positive 1 charge to get the 8. So if you look here, you can see some common ions. 1A is generally going to form +1. 2A is generally going to form +2. The transition metals do not follow this rule. Many transition metals actually have more than 1 charge. So we're going to skip all the way to 3A is usually +3. 4A actually forms covalent bonds, so they don't really make anions anyway, but if we were going to categorize them, I'd say +4. And then we have -3, -2, -1, and again, the noble gases don't form ions either. Anions or negative ions are formed when atoms gain electrons to get 8 valence. So they're going to gain negatives, so they become negative. The way you would show that with electron configurations, here's the normal stable sulfur atom. In order to get 8, right now they have 4, 5, 6 valence, they're going to gain 2 electrons. So where are those 2 electrons going to go? They're going to add to the 3p. So the S2- anion just has 2 extra electrons. Conversely, cations are when you lose negative. This is a positive ion. Same idea though. In order to get 8, they're going to lose some. You're actually going to drop down to a lower energy shell, but the process is going to be endothermic. It's going to require energy. So if we look at the normal stable magnesium, it has a total of 2 valence electrons. It is going to lose those 2. So this entire orbital goes away. And we're just going to look at the 2p. Actually, here it has 8. There's 2 ways you can write this. Here, it's just showing you the 3s is completely missing. Some other ways you could write it is write the 3s with the 0 there, showing that that orbital is empty. Atomic radius, very simply, is the radius or how big an atom is. There's a number of different ways of doing this. One thing you can't do is just take a normal atom, single by itself, and measure the size. And that's because that the boundary of an atom really isn't normal, and it really only contains 90% of the electrons. So you can't do it just plain. You have to basically bond it. Van der Waals radius is an estimation with non-binding, but you're not going to find that very often. Most of the time you're going to find a covalent or bonded radius when it is bonded together and you do half the distance between the covered nuclei. So to the left here, notice the two bromine atoms are bonded. The electrons become stable when they're bonded. So what happens is we find the distance between the two nuclei and we cut that in half. And that gives us the radius of each atom. The van der Waals is shown on the right here. Notice they're not overlapping, but they're still kind of in an orderly pattern where the electron shells are going to be very stable. The trend is that atomic radius increases down a group and decreases across a period. The reason, and this is a big part, the reason atomic radius increases down a group is because you're getting into a next valence shell. You're going higher and higher into subsequent shells. So in period 1, you have one shell. In period 2, you have two shells, and obviously, it's going to build on each other. It decreases across a period because you're adding electrons to the same valence shell and the effective nuclear charge increases. That means the shell is being pulled closer and closer and closer and closer. Remember I talked about this effective nuclear charge is a huge component. You need to be able to explain this using the term effective nuclear charge. For transition metals, they increase in size down the group, but really they are pretty much the same across a period. For much of this, the transition metals don't really apply. There's much less difference because almost all the electrons are going in the D block, and the D block is pretty much similar. The effective nuclear charge on the Ns2 electron is approximately the same across the D block. This graphic is showing you the differences in atomic radii. Notice it's very ragged. It is not like it's going up or down by one at a time. It's very jumbled, but in general, it's following the same pattern. That pattern is shown here. So left to right, radius decreases, and then bottom to top, it increases. So the easier way, I think, to look at it is top right corner is the smallest atoms, bottom left corner is the biggest. Notice in the D block, they're all relatively the same size. You may be given two elements and have to figure out which one's smaller or larger. It's all about their location. Remember, the biggest is in the bottom left, smallest top right. Cations form when the atom loses electrons. For transition metals, this is not always very clear. For some transition metals, the may be removed from the sublevel closest to the valence shell. So if we look here, a normal aluminum atom, there's its configuration. This is the stable state. When you form a +3 ion, you're going to lose 3 electrons. And if you notice, this one actually is quite normal because all the ones in the 3 are lost. But if we skip down here, here's the normal iron. Iron's going to lose 2. If we look, the iron does not lose them from the 3D because that isn't the valence shell. The valence shell is the 4s shell. So the 2 electrons that are lost are right here. It's missing. 2 ways you can do it. Like this, just completely delete it. Or you could actually write 3s2, 3p6, 4s0, 3d6. Look here. It's the Fe plus 3. It actually loses 3. Notice it's going to lose the first 2 from the 4s. Then the next one in line is going to be the 3d. And you can see the same following trend with the copper. It's going to lose the one in the 4s. That is the valence shell. Electron configurations, these up and down arrows can tell you a lot about a magnetic field. Whenever you have unpaired electrons, especially in the D block, you get something called paramagnetism. That just means it's attracted to a magnetic field. It's basically a fancy word for saying it is magnetic. That occurs when you have unpaired electrons. When all the electrons in an orbital are paired, you say it's diamagnetic, or really, it's slightly to none. It's basically not attracted to a magnetic field. You also have something called ferromagnetic, which means very strongly attracted to a magnetic field, and that has to do with the number of unpaired electrons. Ionic radius basically is the same trend as atomic radius. Instead of the size of an atom, it's the size of an ion. Again, it increases down a group. Very much same trend as atomic radius, and the reason is the same, the higher valence shell. One important fact, though, is cations are smaller than the neutral or original atom. Anions are bigger than the original atom. The exception here is rubidium and cesium. They are bigger or the same size as fluorine and oxygen. Larger positive charge means a smaller cation. An isoelectronic species is a species with the same electron configuration. So you can actually have two elements, two atoms that have the same electron configuration because one's a stable and one's an ion. The larger the negative charge, the larger the anion. The next topic here is ionization energy, which is the minimum energy needed to remove an electron. Remember, ization always means the process of. So ionization is the process of making an ion. This is an endothermic process, or meaning it requires energy. These two equations here show you, here's the ionization energy, here's the electron coming off, here's the ion that results. It's really only the valence electrons that are removed. The core electrons are very, very difficult to remove. When you remove the first electron, that is called first ionization energy. The second electron is called second ionization energy, and then it just goes on from there. Third ionization energy, fourth. The general trends, as we're going to see, the first ionization energy decrease down a group and increase across a period. This is because of the effective nuclear charge. The more, force the nucleus is holding onto the electron, the more energy, or the higher the ionization energy would be. The farther the most probable distance the electron is from the nucleus, the less energy it takes to remove it. So the farther away the electron is, the less strongly it is held onto. Again, it is not a normal pattern. It is very ragged, but the pattern still exists. So again, if we look here, left to right, ionization energy increases, and then top to bottom, it decreases. So again, left-hand corner, lower left-hand corner is the lowest, upper right-hand corner is the most. Notice the transition metals aren't even here. This doesn't really apply to them. There are some irregularities in the trend. Of course, there's going to be exceptions. Ionization energy generally increases from left to right, but from 2A, 3A to 5A, it gets a little weirder, and here's why. It says, which is easier to remove an electron from the N or the O and Y, and the B or the B and Y. So you see here's Be and boron, beryllium, boron, nitrogen, and oxygen. So if you look, to ionize beryllium, you must break up a full sublevel. With boron, there's actually one by itself. So if you look here, this shell is empty. So to make an ion, you actually have to break up this pairing, almost like breaking a relationship up, which is harder to do. If you look down here, boron has one electron just kind of hanging out by itself in this outer shell. So that is actually easier to remove than breaking up the pair. To ionize nitrogen, you have to break up a half full sublevel, where in the oxygen, you have one that's, when you ionize oxygen, you get a half full sublevel, which costs less energy. So if you look here, 1, 2, 3, you're going to have to take out that electron. Here, you're going to take out here, which is going to create cost less energy, lower ionization energy. The removal of each electron costs more energy. So when you take an electron from a neutral atom, that is always going to be less energy than to take an electron from an ion. Basically, there's a shrinkage in the size of the ion because of the protons. There's more protons now, so it's going to pull the electrons in closer. There's a regular increase in energy for each successive valence electrons removed. A large increase in energy when you start removing core electrons. Core electrons are almost impossible to remove. So if you look here, the first ionization energy of sodium and magnesium is here, and then you see the huge jump in second and third ionization energy. If you look at this chart is very telling. If I didn't have the elements here, you could tell right away what element it was if I gave you the period, because you can figure out how many valence electrons it has. And the way you figure that out is this. If you see this ionization energy and you compare it to the next one, there is a huge jump. The first ionization energy is way less than the second. That tells me immediately that this one only has one valence electron, and therefore I can identify that as sodium. If I look here, okay, it's going to go increase a little bit, but then there's a huge jump here. This has 2 valence, and then here start your core. And same thing as we go, okay, increasing, huge jump, 3 valence, etc. and so forth. Electron affinity is the amount of energy released when an electron is added to a neutral atom, basically when it forms a negative ion. Generally, since it's saying the amount of energy released, you assume it's exothermic, but can actually really require some energy, especially the alkali earth metals and the noble gases. More energy is released the larger the electron affinity. Generally increases across the period, which is not absolute, becomes more negative from left to right. The lowest electron affinity is in the period, is the alkali earth metal. The highest is the halogen. So it kind of doesn't follow exactly what you want, mostly because the noble gases are kind of, or are have 8 valence electrons. So in a way, you can kind of ignore them. So in general, if you're ignoring 8A and you look, it's increasing left to right, increasing bottom to top. So the highest electron affinity is here, upper right-hand corner. Lowest is the lower left-hand corner. Remember, we're ignoring the noble gases. This gives you the actual values of electron affinity, so you can see, if you notice here, 8A is all 0, which is where you can kind of figure they don't really even count. Beryllium and magnesium actually are very small as well. And you can see the differences among the other elements. A metal, remember, is a very unique property. It is malleable, ductile, shiny, lustrous, reflects light, conducts heat and electricity. The best way to think of a metal is think of like copper. That is a classic metal. When you want to describe properties of metals, just describe copper. Chemical wise, they form most oxides that are basic and ionic, and they form cations. They generally lose electrons. They get oxidized. Nonmetals, think of like chalk. They are brittle, they're dull, they don't really conduct electricity. The opposite of that is insulating. Most of their oxides are acidic and molecular, and they form anions, and they are reduced. The metallic character increases left to down. So it's an element gets more metallic left to right and top to bottom. This is just showing you the metallic character within a group. So if we look here, we start with nitrogen, which is the gas, and then we go to bismuth, which is a very clear metal. Opposite way when you go across a period. So we start with sodium, and then we end up with chlorine gas, which is obviously not metallic. Atomic radius increases down the alkali metals. The ionization energy decreases. There is very low ionization energy. This because it doesn't take a lot of energy to remove that electron. They are good reducing agents. They're easy to oxidize. They're very reactive. They are actually not found by themselves in nature. They're so reactive, they're always paired with something else. When they react with nonmetals, they usually react with the halogens to form a salt, and they are generally soluble in water. The electron affinity decreases down the group, so does the melting point. They have very low melting points for metal, and the density increases down the column except for potassium. So if we look here, there's the alkali metals, gives you some specifics, but the trends are there, what I showed you. One cool thing about the alkali metals is they react very violently with water, most of them. Sodium and potassium do very violent reactions that are pretty cool. Halogens, remember, are 7A. The atomic radius increases down the group. Ionization energy decreases. They have very high electron affinities. They're good oxidizing agents, so they are easy to reduce. They're very reactive. Again, they're not found by themselves in nature. They're always bonded with something else. Happens to be they're usually bonded with 1A. They react to form salts, which are generally soluble in water. The reactivity increases as you go down. When they react with hydrogen, they form a binary HX acid. The melting and boiling point increases down the group, and the density as well. So again, showing you some properties of halogen, showing you chlorine, bromine, iodine, some properties there. The noble gases, they're called noble gases because they don't react readily with most things. The reason, because they have 8 valence electrons. In general, the radius increases down the group, the ionization energy decreases. It is very high for all noble gases, but it still decreases as you go down. They are very unreactive. They're only found uncombined, mostly gases in nature. We say they're inert, which means they react pretty much with nothing. I think there's only 3 compounds that even form from the noble gases. The melting and boiling point increase down the column. They're all gases, as we said, and they have very low boiling points, and the density increases as you go down. Again, some properties of the noble gases. And that concludes our Chapter 8 lecture.